the only thing is when he became a superhero, when he got
All right.
hospital, he worked in the hospital with John Hancock.
Yeah. What?
What topics will be on our second?
Everything we've covered. I mean, there's no topics that are excluded.
Up until now, or?
Yeah. I mean, if you'd ask me, is there a training certain one? No, probably not. But you're responsible for everything. I gotta get rid of that one. In other words, from the second test till now, first test till now, what did we cover? Chapter 5, right? Op amps, right? We've done that. Pretty much it.
Op-amp
I watched it when I was a kid. One scene, when that part of his moved to prison, he tried to become a politician. I'm gonna guess mine's the middle.
What did you ask me? Op-amp capacitor?
We're gonna have one of those on the exam.
You can have, the capacitor will be a steady state frequency, so it'll be a complex impedance. I'm not gonna ask you to take a waveform, and if it's a differentiate with the constants that are there. Or an integrator, would you take an input waveform and integrate it. I'm not gonna ask that. But I am gonna expect you to know, if it's a complex impedance, right, like the capacitor is minus J, 100 ohms, and for an inductor it's plus J50, something like that, how to work that into the problem, all right? It means your loads will be complex in nature, instead of just purely resistive. Okay, fair enough? You asked that question. Now, do you have specific questions about the homeworks? Anything? Isn't there? I think I gave you 43 was the additional homework I gave you. Is that right? Yeah.
So I saw this morning at 8 a.m. There was one problem assigned.
Yeah, it was just 43, wasn't it?
It was 9.24.
2-4, all right.
So it was like back, yeah, it was like going back. I wasn't sure if that was right.
I think it should have been 4-2.
Okay.
Take a look at 4-2. Isn't that a capacitor problem?
I didn't do that one.
Before we move into our new topic, because
Question, are those some of the quizzes? Really? Just pass it down. I haven't gotten mine back. Oh wait.
all right. I'm going to draw this up here. I'm going to talk about gain bandwidth product, but I'm not going to ask you specific about gain bandwidth product. I would ask you for the specific gain. For this one, he has a resistor here.
So 2 nines. That's close. That was so messed Let's go to my standard. Nice.
Now, here's the problem. He gives you an input here that's grounded, gives you an output there, and what you're trying to do is find out what V out is based on V in. Now, this is going to be in the frequency domain. Don't worry about the values of R's and C's yet. Put that in at the end. The impedance of a capacitor itself would be minus J over omega C. Does everybody follow me on that? That's just the reactance of the capacitor. When you look at this problem, what I like to do is break it down into input impedance from input to negative terminal and the impedance from the negative terminal to the output. So I like to structure it like this and just put some Z1 here Here's the negative, here's the positive, it's grounded. Then this is Z2. This is V out. This is classic. You know that the current flowing through here would be Vn over Zi, or Z1, right? That current must flow through Z2, so the voltage here is really going to be Vn over Zi, or Z1 times Z2. And the output voltage will be minus that. So V out over V in here would be equal to simply minus of Z2 over Z1. We've done this before. Now it's just filling in what they are. In our case, Z1 is R1, and Z2 is the parallel combination of these two impedances. And the way I do it is take 1 over the first impedance. So it's 1 over, matter of fact, let me do it right here. Z2, this one, is this impedance. And that Z2 is 1 over the first impedance, which is going to be 1 over R2, plus 1 over the second impedance, which makes this plus J omega C. Please watch this. I'm going to show you this a couple of times more probably. This is the way you can simplify and make sense of this fairly easily. I would like a 1 here, so I'm going to multiply the top and the bottom by R2. Doesn't change the problem at all. Doing that means I get R2 on top, right there, and I also get R2 here. And there's a 1 there. You all agree that that's Z2, class? And you all agree that Z1 is just R1, right? Therefore, we get the voltage gain of this one. You can call it the forward gain or voltage gain is equal to minus Z2 or minus R2 over 1 plus J omega R2C. And then it's divided by Z1, which is R1, which makes this ratio just R2 over R1. And that's the voltage gain. Y'all follow me? Now the maximum gain will occur when omega is 0. When omega is 0, it's just over R1. You follow me? And if you were to plot this versus frequency, if this is F, and if you did, you could actually do magnitude of AV here versus omega, if you want. You would see it would stay there. It would stay as R2 over R1 until you hit the frequency, and listen, because this comes up all the time in engineering applications, where this becomes 1, because when you have 1 plus J, 1, that has a magnitude of square root of 2, and that means this is falling down by 1 over square root of 2 in magnitude, and that's called the 3 dB point. How many hear about the 3 dB point, or the break frequency, or cutoff frequency? Or there's a lot of terms. They all mean the same things. It's where the magnitude of this goes down by 1 over the square root of 2. This is a voltage. The power falls is 1/2. It's the square of the voltage. And it's called the 3 dB point. That's way out here. And F3 dB, if you wanted to talk about the frequency, well, then you would say if omega times R2 times C was 1, or if omega was 1 over R2C. I'm just going through the permutations of how to calculate. You follow me? I want to get the 1 there. I want to see where that frequency is. Then I would go ahead and say omega is 2 pi F. So F would be 1 over 2 pi R2C. And that's called the 3 dB frequency, or the cutoff frequency, or any number of terms. After that point, this thing starts falling down. If it's a log, any of your log, this is 20 times the log of this here. Then it starts falling off at a rate of minus 20 dB per decade. You don't have to know this for a test or anything. We're not electrical engineers, but I should help you, give you a little insight into some of the things you're going to be facing in your laboratory work later on. Now, the gain bandwidth product is really this frequency times the gain right here, the low frequency gain. So that means the gain bandwidth product of this circuit would be equal to R2 over R1. It's always a magnitude of gain right there, times the 3 dB frequency was going to be 1 over 2 pi R2C. And you can see really the R2 goes away, and now I get 1 over 2 pi times R1C. And that would be the gain bandwidth product of that one. Does that make sense to everybody? The gain is the low frequency gain. The low frequency gain for this circuit is R2 over R1. And the high frequency or bandwidth, this is called bandwidth from here to here. This bandwidth is really equal to F3 dB, right there. You all follow me on this? Now, the question you have in your mind, you don't follow me? What don't you see? Tell me.
I can't read the slope there.
Minus 20 dB per decade, it's the rate that it falls. It goes 20 dB. This is a dB scale here. If you take 20 times the log of the gain, it's in dB. If you go down a decade, every time you drop a decade, log of 10 is 1, log of 100 is 2. Follow me on this, class? It basically, every time you go down 1 decade, you're going to go down 20 dB. If you just take the log of 10 is 1, right? That's 20 dB. Log of 100 is 2. That's 40 dB. That would be a 20 dB per change per decade. That's where they get that from. You probably had this, right? How many have had this before? You've had in your systems course, don't you do Bode plots, right? Yeah, sure you do. I know you do. Okay. But that would be the frequency. I'm not going to ask you that. I would ask you specifically at a frequency, what is the gain of the circuit, the output voltage, things like that, all right? Yeah.
What's that right there where it says F? Is that F? So,
Here?
Yes.
That's F3 dB. It's called a 3 dB, small d, capital B frequency. And it's 1 over 2 pi R2C. Now, I'm showing you this because this is a very common circuit. Things like this appear over and over again. And without getting into too much detail, a lot of you, I think at some point, are going to be asked to design something that's a sensor that measures something. And remember, you always want to use an operational amplifier to step up the voltage from it. I mean, like, you know, if you have, let's see, in the old days, you remember these long playing albums, vinyl records, right? You had a little thing, was a needle that fell on that thing and vibrated through the grooves. Those vibrations were picked up by a magnetic transducer. It created voltages, a voltage change, very small. Well, when you take that, you would feed it in to an actual amplifier that would amplify it up so you could do something with it. And then after that, you can filter it and stuff like this and amplify it and do all sorts of things with, if you got equalizers, and then do it power amplifiers, the last stage. But it's always the very beginning thing is to get the voltage up to a level you can do something with before you digitize, because everything is digitized these days. You basically jump the voltage up a couple orders of magnitude, then sample it at a very high speed, and it's all digital processing nowadays. Nobody does analog anymore, unless you really want to go on the cheap. But most people don't. As a matter of fact, nowadays, I think everything is going to be microcontrollers or microprocessors and just DSP, digital signal processing of everything. I'm not saying anything analog these days except for the front end on some of the power amplifiers. That's a good one. All right, well, then we move into our next topic, and this is going to be something called diodes. How many have heard of a diode? All right. A diode's really simple. And those that are MEs and aerospace engineers will appreciate it. You know what a check valve is? What does a check valve do? It prevents liquid or air, or I should say, or some gas from flowing in the reverse direction. It can go in one direction, but it can't reverse. In our case, we call it a diode. The symbol for a diode is this. That's the symbol. Now the voltage on a diode is measured plus to minus V diode. Here's how simple this is. This first circuit we're going to do is called the ideal diode. All right, for the ideal diode, right here, that's VD. If VD is going to be positive, greater than 0, then this diode looks like a short circuit. If VD is less than 0, or if you're trying to put current going this way, follow me? If you're trying to push current that way, it stops it. So that means if VD this is an open circuit, so this is VD is going to be got less than 0. Matter of fact, let me do this one. Now that's an ideal diode. We're going to get to real diodes in a bit. But first, you do the ideal. Y'all follow me in this class? It's a check valve. So just to make sure we all appreciate this, we're going to go through a couple of basic circuits. So if I have a circuit like this, plus to minus, say, 5 volts, and I have a resistor here, make that 10 ohms, and I have a diode here coming down, and I have a resistor 10 ohms here, and I want to know this current. Want to figure it out? I want to show you how you think through these problems, and this is trivial. Y'all see this circuit, all right? Now remember, if current's allowed to flow this way, it will, in the direction of the arrow. Y'all follow me, class? So if you have this, when I have this, current wants to flow this way, right? And then it wants to flow this way. Do you agree? If anything, if current flowed, it would develop a plus to minus voltage there. Do y'all agree with that, class? Because I know it's going to develop a plus minus voltage there. I know this thing will be on because it's forward biased. It's VD is plus, right? It wants to flow this way, can it? Yes. So you can replace this with a short circuit. Now when you replace it with a short circuit, by inspection, what is the I there, class? Does this resistance have anything to do?
No.
No. How much resistance is with this? It's going to be 10 ohms, isn't it? 10 ohms goes to ground, so the current I would be 5 over 10 or 1/2 amp. How many see this? All right? It's 1/2 amp. For that circuit. Y'all see this? I'm trying to go real simple with these things. Once you see the logic of it, it becomes trivial. All right? About to go to circuit 2 as soon as you get it down. All right? Ready? All right. Now I do this. All right, and I want to know how much current would flow in this circuit. So, how much current would flow in it? Current wants to flow this way, can it? Yes. Current wants to flow this way, right? Can it? Yes. Current, is it allowed to flow this direction? No, it's a check valve. Current can only flow in the direction of the arrow. You all follow me? Only in the direction of the arrow. So effectively, this circuit, for this circuit, it looks like it's not there. It's an open circuit. Do you all see this, class? How many do? MEs and probably aerospace engineers can appreciate this. This is a simple check valve. You know, I think the one that you guys, the MEs probably have seen in your fluids courses, they take literally something that looks like a ping pong ball, and they stick it inside of a small cylinder, a little bit larger than the ping pong ball. What they do on the other, one side of the ping pong ball, and I call it ping pong ball, it's just a float, they have something that's a smaller recessed area, it's a pipe. Now, on the other side, they'll put like a block, or really just put a straight piece of material through the center that prevents the ping pong ball from closing off on the other side of the pipe. So fluid, if it's flowing this way, can go through. You all know what I'm talking about? It's called, what is it called? There's a name for this. I think it's called a check valve, isn't it? Check valve is, and so it can flow this way, but if it tries to flow this way, the ping pong ball gets shoved up against the pipe and it stops it. And I say ping pong ball, it's a float. That's all it is. Now that's the most common type of check valve. There are much more sophisticated ones that don't allow anything to flow through. And there's things with advanced flaps and all this stuff I've seen. But that is a simple check valve, and this is an electrical check valve. Think of it that way. All right, now, well, how much current would flow, class? 5 divided by 20, right? And that's 1/4, right? 1/4 of an amp. I'm doing it on purpose, real slow, so you can see how, really, the simplicity of this stuff. Now get your problems and stuff related to this. Now, I like this because these are, this is sort of a binary operation. It's on or it's off. There's only 2 states in this ideal diode. So we go through a lot of the possibilities. If you have more than one diode, what happens? We're going to talk our way through these, and I want you to think about it. Remember, I'm going to leave this up here. If it's current's trying to go in the direction of the arrow, can, trying to go in the opposite, it can't. That's all you have to remember for now. So let's do this one. This is the first thing. Well, I'm going to do this one then. And what I'm after is this current I. What would I be there? Just take a look. It's as easy as it looks. Which way is current trying to flow? If the diodes weren't there, trying to go clockwise, right? Is it allowed to go clockwise through those diodes, class? Yes, it's in the direction of the arrow. Do you all see that? So they're like short circuits. Do you follow me? If current wants to go this way, it's allowed to. It's allowed to go that way. So the current here would be 10 over 20 or 1/2 of an amp. Do you all see this? Class, do you see this? This is trying to make it as simple as possible. That's 1/2 for this circuit. Agreed? Keep watching. Very small permutations here. Now I take this one and I do this. How much current flows? 0. I know, it's so simple, but I'm driving the point home. I tell you, no matter how much I do this, somebody will put 1/2 amp for this one. Almost like clockwork. It doesn't matter. They miss something in the lectures. Something doesn't register. All right, that's 0 for that one. Now, the next one gets a little more complicated. Yeah, not a whole lot, but a little. So now I'm going to have 200. We're going to have 100. I'm going to have 500. I'll show you tricks with this too. And I'm going to have a diode like this. And I'm going to have this V be equal to 6 volts. 6 volts. And I want to know how much current flows. Now, it's as simple as it looks if you think about it. Which way does current want to flow?
Across the resistance?
Counterclockwise. Can it flow? Just make this a short circuit. Will current flow? Absolutely. How much current would flow? It would be the parallel combination of this. First it would be 200 and 100 is 300 in parallel with 500. Do you agree with me? So the max amount of current that would flow here would just be equal to 500 in parallel with 300 is 1 over 300 plus 1 over 500. We can leave it like that. I mean, that would be, excuse me, that's the actual impedance of that. And if that's divided, that's actually R equivalent. And if I take I would be equal to R equivalent divided by, it'd be equal to 6 divided by this. When you take 1 over that, you get 1 over 300 plus 1 over 500 times 6. And I'm just leaving it in this form. Got me in this class? I'm trying to show you how simple these are, yet how they can get to you. The next one gets a little more complicated. This is a very simple one. Not complicated. It gets more and more. There's more and more possibilities for the state. So I'm going to get rid of this one with the next one. Next one's going to look like this. I'm going to have 8 volts. And 1K. This is 5K. This is 4K. All right, for this one, if you look at it, I want the current through those diodes. How would you reason your way through this problem? Based on the fact, if current would be allowed to flow in this direction, it can, or in the direction of the arrow, and if it's not, it won't. Now just go through this with me. How would you reason it out? Let me ask you this. Can current go this way? Some current, is that allowed? Yes, right? And that means this one can be replaced by a short circuit right here. Now, current would also like to go this way, can it? No, this one would be an open circuit right here. It's that simple. If that's an open circuit, can any current flow through this one? No, and all the current's limited by that. That current would be simply 8 over 6K. You all see that here? I want to show hands, how many do? All right, this diode would be off. Agreed? And now, I'm trying to work my way into something that's a little more complicated without first, I want to first go through these steps of it. The next one I'm going to do is going to be a bit more complicated. But matter of fact, I'm going to erase this. It's worth doing. I'll send these to you today, but this is 1021 out of the problems I'm about to send you. do. We're going to say this point is V out. These are all voltages with respect to ground, remember. This is V in. And what I want to do is go ahead and say for any V in on this axis, this is 0, I want to get V out on this axis. Now this one, you're going to have to I'll explain how to reason your way through it in a second after you draw that. All right. The first thing you always do is with 0 volts coming in, what happens? Well, 0 volts comes in means that's a short. Follow me? That's literally putting a short there. That's 0 volts. At that point, you have to ask yourself this. Can current flow this way? Class?
Yeah.
Yes, it would be allowed to flow that way, right? If it did flow that way, what would the voltage be across this? 0, right? It means if it's 0, the voltage here is 0. That means there is 0 volts here. Does that make sense to everybody? Yes, sir.
You're saying the voltage from V1 across the diode?
No, this is V1 to ground is how the voltage is developed, right? From here to ground is 0. It's a short. And that means if that's a short, current would like to flow this way. Can it flow that way? This is the way you reason it. Yes. If it can, what's the voltage here? 0, right? Because the diode looks like a short circuit. Does everybody follow me on this? How many did that? All right, you follow me? If the diode's on, it's a short circuit, isn't it? Whatever voltage is on this side is on this side, right? Now that's 0 volts. Now listen to me carefully. If that's 0 volts, which way would current want to flow from this battery? Up, right? Is it allowed to flow up? No, the output voltage is 0. Do you follow me? So it's 0 and 0. There's our first point. Now, here's the deal. As V in here starts increasing, all right, listen. As it starts increasing, this diode will still be on until we go above 2. Does everybody see that? How many can see this, right? As long as this voltage is less than this voltage, the preferred path for current will be this way, right? You all follow me on that? Because if this voltage is greater than 2 volts, then current can go this way. Do you all follow me? Class, with me on that? This is important. So now, when this voltage, right, it's going to keep going up until it hits 2 volts. And it's going to go up linearly. Well, not drawn very linear, but. This would be 2. Now what happens at 2? Let's listen. At 2, when it hits 2 volts, right here, V1's 2, it means current is now, well, it looks the same flowing this way or that way. If this is 2 volts, this is just on. You all see this? When it hits 2 volts, that one just turns on, right? What happens if this is 3 volts? Which way does current want to flow? Down, right? You follow me on this? It wants to flow this way. Is it allowed? Class? No. Which means this voltage is what's called, it's limited or clipped at 2 volts. No matter what the input voltage is after 2 volts, it will not change the output voltage. Do y'all see that? The thing limiting the output is this. Y'all follow me on this? How many see this right here? Come on. Do you or not? All right. I'm trying to do this as easy as I can. Think back to this case. When we had the short, everybody agreed the current could flow this way, right? And it couldn't flow that way, right? It would like to, but it couldn't. Do you agree with me? All right, this diode's off, that one's on. Now, keep listening. When you hit 2 volts right here, this looks just like this, right? This is the beginning of the transition. Now, if this voltage here goes greater than 3, right? Well, then this diode right here, if this is greater than 3, current would want to flow this way, right? Because that's only 2 volts there. But current can't flow that way because it's going against the diode. You all see that, class? Following? Don't let yourself get messed up with that up there. If this is you put 3 volts here, right? And there's 2 volts here. Current would like to flow that way, right? These diodes are either on or they're off. Do you all see that, class? And then what would happen is this diode would be on, it would shunt all that current there, but this diode would be off. And when that's off, it means the output voltage will be limited to 2 volts. All right? It will be flat 2 volts forever after that point. It'll just be like this. It's limited to 2 volts and only 2 volts. Now, they're going to have a lot of different ways to do this. One of the things is, when you take a look at the diodes, you're going to first, you can just remove, well, you can't remove both. Remove one, see what the voltage is here, see if current can flow. Then remove the other, see what the voltage is here, and see if current can flow. If the voltage, when one of these 2 diodes is removed, or if this one is removed, and you get a voltage, say call it V1, and this one is removed, you get a voltage here, call it V2. Whichever voltage is less, that will be the configuration to go with. All right? Some of this you got to play with, yes, sir.
Can you do it again step by step?
Yeah. I'm trying to talk my way through this to not make it complicated, because remember, these are binary decisions. They're either on or off, right? Think of it this way. If we had this set up like this, forget that for now. What would the voltage output voltage be? Just tell me. Is the diode on? Current wants to flow that way, right? It's flowing in the direction of the arrow. Do you agree with me?
Yes.
If the diode's on, what's its impedance? 0, right? The voltage on one side is the same as the voltage on the other side, correct? Right? And that voltage would be 2 volts right there, right? Now, if I have this, if I put this diode back here, if it's a short circuit, right? If it's just short, that's the input voltage, right? If I short that, that's 0 volts as the input, right? If I have 0 volts there, well, I knew it was 2 volts would be developed there before that diode was put in, right? But when I put the diode in, because that 0 volts current can flow this way, it'll bring the output voltage down to 0. Does that make sense to everybody? Give me a show of hands if you understand that part. I put the diode in, it looks like a short circuit, right? All right. Now, let's do it. Yeah, you with me? All right, now, I said the transitional part was when it hit 2 volts. Now I'm going to do this. I'm going to make the input voltage here, this is Vn, be 3 volts, all right? I'm going to make it 3 volts, just listen. Make it 3 volts, and I'm going to take this out for now. I'm just going to take it out. And I'm going to ask you what the output voltage is. What is it? It's 3, right? 3 volts. Now, I put the other one in, right? The other diode back in. What value of voltage did this one come to?
2 volts.
2 volts, right? Is it allowed to go to 2 volts? Current would flow this way, right? Now, to maintain that 3 volts, current would have to flow this way, wouldn't it? Can it flow that way? No, it's stopping the flow of current that way. Whenever current tries to flow in that direction, it's stopped. So whenever the voltage on this side becomes positive with respect to this side, it stops. Do you follow me on that, class? And you can see that happens after 2 volts. If you just take a look at this, as long as this voltage on this side is greater than that voltage, this is on, right? Right? But as soon as that voltage is less than the voltage on this side, it's off. And that's when you get 2 volts. And then from then on, it's just going to be flat. Do you all follow me on this, class? As a matter of fact, let me just go a step, yes?
Obviously, at that transitional period where they're both 2 volts, would the current split equally between 2 branches?
Depends if they're identical diodes. There's more to that question, but don't worry about that for now. It's a loaded question. For now, yeah, it's evenly divided if they're the same. And this is the type of thing that's important to see by it. So I'm going to put just V in here, but hang on. And this is going to be plus the minus V in, ground that. And there's my diode. Because remember, it stops current going that way. And the reason it stops it is the voltage, if you take the element out, if the voltage is developed in the opposite direction across there, then it'll stop it. So this voltage is limited to 2 volts. As a matter of fact, Whatever the input voltage is what the output voltage is for anything less than 2 volts. Okay, class, y'all see this? All right, this is a good problem, but it's more of a thought problem. You got to reason your way through this. Now, all right, the next thing I want to do is show you circuits that are called rectifying circuits. How many have worked with diodes in here? Electrical diodes? What did you build with them?
Just rectifiers, AC and DC.
What did you do?
Um,
What?
I just manufactured it well.
Rectify, diodes are used for several things, but one of the things they're used for, and this is important for everybody involved with any kind of hybrid cars, battery powered cars, actuators on planes, a lot of drone stuff too. Diodes take AC voltage and make it DC, and I'll show you how. If I have an actual signal, plus to minus, this is AC sum, V naught right here. So I've got an AC signal. Then you can put it at 100 hertz, it doesn't matter. I have V naught. Now I want to make this AC, right? Here's one way to do it. This is first, I want to just get one polarity of voltage out, you might say. So one thing I can do is this. I put a diode here, and then I put a resistor here. And this is my output voltage. Now, I'm going to show you what happens. The input voltage, if it's V out, looks like this, something like this. It's going to be sinusoidal with a certain amplitude A. This is versus time. You all follow me on that? That's just the input voltage versus time for an AC signal. Now, what does this diode do? It will allow current in this direction, will it not? Agreed? But it prevents current in that direction, doesn't it? So what happens? When you go through this part of the cycle, the output voltage will literally, it'll actually track the input voltage. Do you all see that? But now when it goes on the negative side, now current's trying to go in this direction. You with me? It can't. So it'll be dead through here. And then it'll look like this. And dead. And then another one. Follow me? So what you're left with on the output would be this. That's called half-wave rectification. Does that make sense to everybody? Only half the wave is rectified. What if you're on the cheap and you want to do something and you want to get a DC voltage out of this? Then what you can do is put a capacitor here. All right? I'm going to show you how to calculate certain values in a second. What that'll do is the voltage will charge up to this, and then it'll slowly decay, charge back up, slowly decay, and charge back up. Do you all see this, class? This is half-wave rectification. It's okay, but it's not ideal. Do you agree with that? So then there's something called a full-wave rectifier that I'm going to go through next. Now, how many see that circuit causes this waveform? Just to show of hands. Everybody? All right. It's very straightforward. There's nothing tricky. The diode is like your check valve. And there's plenty of MEs and aerospace engineers in here that can appreciate that, right? So draw the parallel that way. Now, after that, it's full wave rectification. I like showing this, I like to show the practical uses of these things as soon as possible. So I'm going to try to show you this now. This is full wave. With full wave rectification, what we have is this. Remember, that's still AC. And now what happens is, you're going to have one point that current's allowed to flow to, no matter what cycle. If this is the positive half of the cycle, it'll flow this way. If it's the negative half, it'll flow this way. On the other side, it's going to have something where current can only flow out of this. And you'll see what I'm talking about in 1 second. I'm not being very clear, but I hope you just appreciate that. Actually, let me do it this way, so you see it better. Now, just bear with me on this one. We're going to take a look at this output voltage, or call this VN, pardon me. VN versus V out right there. Can you all see the circuit I've drawn? All right. When I do this, first I draw the input waveform. This is going to be VN. That's the input waveform. And it's got a height of, say, A. Negative height A. By the way, this is a circuit. How many have built a rectifier circuit like this, a bridge circuit? Anything like this for rectification? I've had to do this. The one thing we had a railgun project where we had to take about 10,000 volts AC transformers in for a neon sign, and we had to rectify to make it DC. You follow me? Because we had to be able to get about 10,000 volts DC to charge a capacitor back. Now, so I mean, we just had 110 out of the wall. We didn't have any large voltage sources. So what we did was this. I know about out of time, but listen, we use this, but the big problem is each one of these diodes has to be able to withstand the maximum voltage that you have, because it's going to have to block it. So these have to have a breakdown voltage at least twice the maximum that they're going to feel, or else they'll blow, and we did blow a lot. And that's a tricky thing, by the way, and I'll get to that in a minute. So what does the output voltage look like? All right, when this is positive, right, current wants to flow this way, wants to flow down here, and then wants to flow back this way. You follow me? Here's the path if it's positive. It'll go here, up, this way, this way, this way, this way, and back. You all see that? Let me just finish this thought here. So it can, so it'll track. Now, what happens when it goes negative? When all of a sudden this is positive and this is negative, all right? Well, when that's positive, current wants to flow this way. In fact, it can. Comes here, it'll make this V naught positive, but then, remember, it wants to go this way, then it flows this way, all right? What's the reverse voltage? And it causes this. So now it takes both parts of the pulse and puts it makes it positive on the output. Then you put a capacitor across there, and there's some other tricks, but you can make, that's full wave rectification. And some of you are going to deal with this, and I'm going to tell you one thing. With this, if you ever build these diodes, each one of these should be able to withstand twice the actual peak voltage here. At least that. If not, you're going to run into all sorts of trouble. And I have, personally. Yeah? Not diodes. All right. It's going to be on outputs. Okay?
And will the test on Wednesday cover diodes?
Yes.
Okay.